Hey everyone, and welcome to the final video of our electronics tutorial series. My name is Aaron from AX Electronic, and today we are going to look at BJTs one last time and look at how we can apply them in current mirrors. So if you remember from our MOSFET current mirror video, we said that a current mirror is something that can take a reference current that we can generate using just a resistor and a transistor, and it can mirror that current to multiple transistors so that they're always drawing the same amount of current. So we can take this reference current that we can generate fairly easily and extend this to multiple other circuits. That way, for example, if we need a 10 milliamp current source, we can generate that relatively well further downstream in our circuit. So these are a whole lot easier to analyze than our MOSFET current mirrors. So let us go ahead and jump right in. All right. So again, if you don't know this by now, this is our NPN BJT. So this is an NPN BJT. And whenever we have current flowing from the base to the emitter, a larger current will flow from the collector to the emitter. So the collector current is going to be equal to beta times the base current. Now, BJTs, like I said, lets us derive some pretty intuitive equations for these current mirrors, whereas MOSFETs, we had to rely on a lot of semiconductor physics knowledge, stuff like that. For BJTs, we can take some very simple models and make some pretty accurate current mirrors just using those simple models. So let's take a look at this first configuration here. So let's say that our VCC, let's say that this is just 10 volts. Okay, so for this example, we'll assume that this is 10 volts. And I'll just call this one R for now. Okay, so this is just a resistor. We're not sure what exactly it is yet. And let's see what's going to be happening here. So we're going to try and figure out what the current is at all the different points in this circuit. Okay, now remember, unlike MOSFETs, our BJTs have a base current that is non-zero. Okay, so there is going to be a current flowing into the base. Now, the first thing that you should be saying right now is that, well, we know that there is this 0.7 volt drop from the base to the emitter, and our emitter is tied directly to ground. So if our emitter is at 0 volts, and we're assuming that this BJT is conducting current, then there must be 0.7 volts on our base. Okay, so there must be 0.7 volts on our base here. And that means that there's 0.7 volts on our collector because our base is tied directly to our collector. Now, if we know what our supply voltage is, then we can calculate the current flowing through this resistor based on these two values. So if we know this current flowing through the resistor, I'll call this IR for the current through the resistor, it's going to be the voltage drop across that resistor, which is our VCC minus 0.7 volts over our resistor. Now, the current through this resistor is split off. So we have a base current and a collector current. So this IR is equal to our collector current plus our base current. Now we know that our collector current is just beta times IB. So we know that this IR is going to be beta plus 1 times our base current, okay? So we can actually, if we actually write this in a little bit different way. So instead of saying that our collector current is beta times IB, what we can do is that we can say that our base current is actually IC over beta. So now we know that our IR is equal to IC plus IC over beta. And that's just going to be IC times 1 plus 1 over beta. Okay, so that is going to be the current that is flowing through that resistor. And you'll see why I used IC here in a minute, okay? So what we can see is that using these two equations, we can solve for our collector current fairly easily. So we have, this is our IR is IC times 1 plus 1 over beta. And that's equal to VCC minus 0.7 volts over our resistance, R. So if we know our VCC, we know the IC that we want because that collector current that we want is going to be mirrored to our other circuits, then we can actually solve for this resistor that we need. So using only a resistor, we can tune this current mirror to draw a specific amount of current. So let's look at an actual example here. So let's say that this is a 10 volt supply and we want our reference current to be, so our IREF, we want it to be 10 milliamps. That means we want this BJT to draw 10 milliamps no matter what it's connected to further upstream, as long as it's not violating the laws of physics. We're going to have to select this R in order to draw this correct amount of current because we can't change the properties of this transistor on the fly, but what we can do is we can change this resistor. So let's set up this equation. So we know that this is 0.7 volts here. And we know that there is an IB flowing this direction and an IC. Now the IC we want to be 10 milliamps. So we want our IC to be 10 milliamps. Now let's set up the equation that we had previously. So if we look back a slide, we can see that we have IC 1 plus 1 over beta, and that's equal to VCC minus 0.7 volts. Where's my, there we go. VCC minus 0.7 volts over R. Now IC is known. Beta in this case is known, so let's assume that beta is about, let me scroll down to my notes so I can make sure that we're using the exact right thing. Let's just say that beta is about 100. So we'll say that beta is about 100. So that means that in order to solve for R, well, we can just skip a couple steps here. You can do the math on your own. R is going to be equal to this voltage drop across the resistor divided by IC times 1 over 1 plus beta. And again, we know IC, we know beta, and we know VCC. That means that we can solve for this current. Okay? So in this instance, we actually have another little bit of current that we haven't taken into account yet. So if we look back here on a previous slide, what we'll see is that we have just this one IB. Okay, so we only have one transistor that's drawing current. In this configuration, we actually have to draw current from this transistor and also this second transistor. So that means that instead of having IB here, we're going to have 2 times IB, and that's actually going to be reflected here. So instead of a 1 over beta, we're going to have a 2 over beta. Now we can actually make a little bit more of a general form here. So what we can do is that we can solve this equation here. So VCC minus 1 over N over beta, IC times R minus 0.7 volts equals 0. So if we solve this equation for R, where N is the number of transistors that we have in this mirror, then we're going to get a nice general equation. So in this case, Rn was 2. Okay, so we have this 2 over beta here. Now, let's plug in some values. So let's say we want 10 milliamps here. We have a 10 volt supply. Then what that is going to cause if our beta is 100 is that that is going to end up giving us an R that is equal to 912 ohms. So if we have a 912 ohm resistor, that is going to cause 10 milliamps to flow through this transistor. And then because it's mirrored and we're assuming that everything is just about symmetrical, that means 10 milliamps is going to flow through our second transistor, no matter what is upstream here. Like I said, as long as it's not violating the laws of physics. So this setup works fairly well. There are definitely other types of current mirrors out there that provide a little bit more robust control that maybe doesn't vary as much with the load, but this is a good introduction to using these BJTs as current mirrors. So let's check out some simulations so that we can see exactly how this is working. So I have this very basic simulation set up right here. Now you can see that we have this 10 volt supply, and instead I'm going to change this to that 912 ohms that we saw previously. So if we look back in our slides, we were using 912 ohms. So that's what I'm going to use here. So 912 ohms going into a 2N2222, and this is also being mirrored to another 2N2222 that has this 5 volt supply here. Okay, so instead of having a resistor or a network up above it, we just have this 5 volt supply to see how this is going to behave. Alrighty, so let's go ahead and run this simulation. Now let's check the current that is going through this 912 ohm resistor, and then we can see that it's about 10 milliamps, about 10.18 milliamps. Now if we look at our collector current down here, it's even closer to that 10 milliamps. And over here on our other transistor, we can see that we're drawing about 10.47 milliamps. Now you might be wondering why there's this inaccuracy. Well, let's take a look at the voltage. So in this instance, this transistor has about 0.7 volts from its collector to its emitter. Okay, so this transistor has that 0.7 volts from its collector to an emitter. On our second transistor, our voltage is all the way up to 5 volts. So it's kind of like the transistor wants to supply that same amount of current, but because we have a much higher voltage, it's kind of just pushing through there. So that current is pushing through there, it's forcing more current, just a little bit, which is why we get this slightly higher current. So if we change this to something like 930, and we rerun the simulation, what we'll see is that this collector current is now a little bit closer, okay? And we can tune this to be exactly how we want. Now, I'm going to switch this simulation command up a little bit because what I want to show you guys is actually the effects of this supply voltage here, or of the collector voltage here. Because like we saw, having this 5 volts here instead of this 0.7 volts we have on our other one is going to cause a little bit of a discrepancy in the amount of current that's drawn, right? So it's a little bit of a discrepancy, not that major, but it is still something that we have to take into account if we're using some very precise electronics. So instead of a transient simulation, what I'm going to do instead is I'm going to run a DC sweep. So for the first source to sweep, we're going to sweep the collector voltage here, V2. It's going to be a linear sweep. We'll start off at 0 and let's go to 10. And we'll use the increment of 1 millivolt still. Now if we run this simulation instead, you can see that at 0, like we kind of anticipated, there's not going to be any current flowing through this transistor because, like I said, we don't have any voltage that's actually pushing through it. But as we increase this collector voltage, it's going to be pushing more and more. Now if we change our sweep to maybe see a little bit in finer resolution, if we go from 3 to 10 instead, what we can see is that as we increase our voltage, or as we increase that collector voltage, it's drawing slightly more current. So it's not 100% stable or 100% independent of the load, but it's pretty close. So if you need something that is not very sensitive, then you can definitely use this configuration. If you need something that's a little bit more sensitive, you can use some different types of current mirrors that may give a little bit better performance, less dependence on the collector and emitter voltage. So I hope this has given you a good little introduction to current mirrors, and I hope that you've enjoyed this electronics tutorial series. Now that if you've been following us throughout this whole series, I think that you've kind of reached the point where you have a good general understanding of electronics. You definitely don't know everything because I don't think anyone really knows everything that there is about the whole world of electronics because it's very deep, very broad, so it has a very much depth and breadth. So it's going to be very hard to learn everything, but this is going to give you a nice general introduction. If you want to see more content or maybe some more detailed content, or if you have detailed questions, please let me know. I'm happy to make some detailed videos of talking about maybe why this specific type of current mirror has this behavior and how we can fix it, or maybe how we can get different types of amplifiers going to do different sorts of things. So, as always, if you have any questions, please feel free to leave them in the comment section below. If you like this content, please give me a thumbs up and subscribe to see more. Even though we've reached the end of our electronics tutorial series, I'm working on some new content for us. That way we can continue going and continue learning and never stop this adventure of learning all that there is to know about electrical engineering. So, other than that, thank you guys for watching, and I will see you next time.